And the great thing about subsystems is what they do is they hide the complexity. So we went through an example yesterday whereby you created a subsystem of a fairly simple block anyway, but of course, as you'll see for your assignment next week, you're taking the house code and you're actually creating a number of subsystems within that. So we showed you how to create one, how to propagate the signal names. As an aside, I showed you how to reduce signal congestion, and then we looked at the subsystem. And in particular, we were moving towards a point whereby when you're running a model and you want to be able to run the model multiple times, and each time you run it, you want to change a parameter, which you don't want to have to do with going into a script, changing the line in the script, saving the script, and then running it. You want to be able to do it dynamically. So we use what's called a mask for that. So one way of doing it is changing the value here in the base workspace, and that value is the integrator initial value. But masking is a much better way of doing it. So I showed you how to build a mask. This is where we kind of finished up. So with the mask you have to specify a number of things. The most important one here is the parameters and dialog. So essentially, when you click on that subsystem, which is now masked, you'll get a prompt coming up. And in my case, the prompt will be integrator initial value with a colon. And whatever value you type into the dialog box will be assigned to a variable called initial value, which, as you know, is the gain on the integrator. Alright? So it's a much nicer way of being able to mess around with variables and see the impact on the fly. Some people would say it's a bit of a positive, but actually what it does is it adds another layer of complexity. So I said in terms of workspaces, you've got the base workspace, you've got the model workspace, and now you've even got a mask workspace. So what it means is that that variable initial value no longer appears in the model workspace because it's actually hidden within the mask workspace. So I hope that makes sense. And if it doesn't make sense, it will cause you confusion when you're running your model. You're wondering where are the variables coming from. But you need to be aware of that hierarchy in terms of where Simulink looks for variables. Okay. So that's the most important part, the parameters and dialog. The rest of them really are just about window dressing. So we've got the initialization. So in other words, what would appear? When you start it up, you have integrator initial value is some value, and then that string is displayed as part of the icon. So in other words, what you will see when you run the model, and that's just some of the documentation stuff. All right. So in other words, those three and this one dialog, they set the four different aspects to the mask. So when you run the code, you see all those. So there's the dialog box coming up. There's the value you enter for the initial value. There's the prompt, and there's the other details here that you've specified here. And there you see the display. Integrator initial value is 4. And sure enough, there's 4. Okay, so a very nice way to make your changes. As I said, the only complication is that that value is no longer in the base workspace. It's set within the mask workspace. Okay, so in this case here, this is where the alarm went off. So you can see here we have a variable called initial value, and in fact we have two of them. I'm setting the initial value, which is the variable used in the integrator, remember? And I'm setting it to 100. So in the base workspace you see here, the initial value has a value of 100, that variable. But when I run the model, remember this dialog box comes up, and it asks me for a value, which is assigned to initial value. But remember that initial value, INIT value, is not this one. This one stays at 100, the reason being that the mask for the integrator now has its own variable called initial value, which is hidden from here. and it's actually equal to 9. So when you run that code, it starts at 9 and not 100. So just in case that causes confusion, make sure you get your head around that. Okay, one of the other things that I want to run through is very quickly how to run scripts within scripts and how to run a model from within a script. So, what I have here is, and I put this up on Blackboard. So as you can see, we have a sine wave generator. There's the bias. So in other words, we're starting off at 5. I forgot my bloody marker. Does anyone have a whiteboard marker, no? Yeah, I could try and set up this thing, but it will take about a week, so I'll try. So essentially we have a sine wave that starts off, we'll see it in a minute. Okay, can you see this? Okay. So this is the 0, so there's 5, and you have a sine wave around that with an amplitude of 5. We're integrating it, and then we're showing the details. Now, what do I want to show you here? Okay. The integrator, again, has an initial value set here. So what I want to show you is, sorry, this one doesn't work today because I don't have enough. That's one problem with the Macs. They don't have enough USB ports. Okay. Right. So this is a piece of code called call within script. Right? This is it here. By the way, some of you are forgetting the H1 lines. Call within script.m needs to be on the top of your script, which is the same as the name of the file. Okay. So when you run this script, what happens is the first thing it does is you're telling it to run another script. So use the command run. So you could have done this for lab 6 for the equivalent value for the house and the mass of air in the house. You could have just said, let's call lab 5, which reads in all the details. But I said you didn't need to do that. You could just actually set the R value and the mass as constants in your lab 6. But if you wanted to, this is another way of doing it. So you're running a script within a script. So as you can see, when you run this script, what does it do? It's a very simple script that just sets a variable initial value to 10. So when you run this script, the first thing that happens is it runs another script which sets a variable to 10. The next line then is you now want to run the model. So you use the sim command to run a model within a script. You give it the name of the model, and you can give it the runtime as well, if you wish. Okay. Otherwise it will be set, whatever is set in the model.
That's you.
Yes, lads?
So bless you because he sneezed.
Sorry?
I said bless you because he sneezed. No question, it's fine.
No religion in this lecture.
Whoa.
I'm joking.
Storm also. You're on camera.
Oops. This is like getting in trouble over that. Okay. Alright, so as you can see here, I'm calling that script. And it sets the initial value, and then it starts up the model, and the model runs for 10. And as you can see, here is the sine wave. As I said, it has a default of 5 plus or minus 5. And here is the integral of that. Okay? So very useful in terms of setting parameters within the script and then running the model from within the script as well. Okay. That's all I wanted to say about that. Now we won't actually be doing that, but again I wanted to show you how you do it. Now please, do I have... Okay, so based on all that, presuming you all understand all that, this is what you have to do for next week, right? So next week is the last lab. Lab 7. And I'll talk to the class reps, but what I can do is, if you wish, is run labs the following week. If people would like time to, particularly the engineers, I suspect, we've got an exam coming up in a few weeks. So, not too sure if there's any value to the IT guys, because their exam isn't for X months. But is the engineering class rep here? You do have a class rep, don't you?
Yeah, he's the French lad.
Yeah, okay. How many engineers do we have here? Okay, hold 3. Okay, 4. Are you engineers as well? Right, 4 of you. Right.
Represent.
Okay. Oh, I meant to show you the results for Lab 4, by the way, were a hell of a lot better than Lab 3, as you suggested. They still weren't great, mind you. But the attendance, in terms of what was handed up, was a lot higher. And the marks were generally higher as well. You got those, did you? Had they posted yet?
Yeah.
Yeah, I got the summary of them anyway yesterday, so I suspect they're all. Alright. Okay, so Lab 7. So Lab 6 is building the Simulink model, right? And you built the script in Lab 5 for it. Okay? Or part of the script that runs the R value of the mass affair. Okay. Lab 6 then builds the full model, and then Lab 7 uses the very same model you've done. The one with the external temperature model is a sinusoid, the simple one. Okay, not the one that reads in temperatures from the Excel spreadsheet. So Lab 7 is built using that model. And all you're doing is you're packaging the various components into subsystems, like we've just seen here. So use subsystems to simplify the appearance of your house model from Lab 6. In particular, I want a subsystem for the thermostat and heater, a subsystem for the external weather, which is really just a sinusoid with bias. It's really simple, really. And a subsystem for the house. Okay, so your model will look a little bit less cluttered because you're just putting everything into big blocks. However, I then want you to mask the subsystem for the weather. And the reason I'm doing that is that I want you to run your model a whole load of times, and each time I want you to change the parameters for the weather. And I want then you to see the impact of changing the weather on the energy cost for heating your house. Alright? So develop your mask so that you can enter both the baseline temperature and the variation. So if we look back on, well, I don't have my marker. Sure. I'll show you. That's not one color. Okay. So essentially what I want you to do is when you set up your external temperature. So your external temperature will be some baseline, which in this case is 5, and some variation, which in this case is 5 as well. So in this case the temperature is varying between 10 degrees and 0. So I want you to set both of those parameters as variables. Right? So when you define your external weather subsystem, of course you have a sine wave, and you'll have a bias, and you'll have an amplitude. So set those as variable names, and then what I want you to do is create your mask so that when you click on the model and click on that mask, or that block, what will happen is the dialog box will come up and it will ask you to enter both of those values. Alright, both the baseline, which is the bias, and the variation, which is the amplitude. Okay, run it for 1 week. As before, write a script that runs within your model, etc., etc. Run your model 5 times using different temperature ranges, and then in your PDF report, just show the 5 different temperature profiles and the heater cutting in and out, and the energy cost, and then take the energy cost value off the model and just show me how the energy costs vary depending on the temperature profiles. Alright? Okay? And that's the end of your labs. Alright? Okay. Now to finish, I want to show you this. Okay, I said I would go through someone said lab 3 particularly. So this is Raymond's solution. Raymond does out solutions every week for the guys, the tutors, so they can advise you in the labs. And he spends a lot of time at them. Puts in more comments than I would even, indeed. So anyways, so this was lab 3, which was probably the most complex of the labs. So tidy up, okay? Input the name of the file. Remember, this had December temperature per minute, right? So it had 40-something thousand values, right? I have it here, actually. Okay. $44,641 values, alright? Okay. So read in the name of the file, and now we want to extract the temperature every hour. So the funny thing I noticed here is that there was an error when I ran this code this morning, because the Excel spreadsheet is as follows. Alright, so there's the Excel spreadsheet. So you've got the timestamp, you've got the temperature, humidity, etc. But in fact, MATLAB is converting that into a number. So in other words, the ones we're interested in is the second column, which is the temperature here. I suspect it depends on the version of MATLAB. But anyways, that caused an error for me this morning. So I had to change 1 to 2. So essentially you're extracting all the temperatures for the whole month in this line here. Then you want to extract the temperature at the start of every hour. So every 60th value. So the first value, the 61st value, etc., etc. So what you want to do is create an index first, which will, how am I going to say? Will create, so this vector here will have values going up in 60. And then you read those values from the temperature file. So essentially temperature 1 will be the temperature at the start of every hour for the full month of December. And then we plot it. Okay? So we plot the temperature. Then remember I asked you to find out the minimum and the maximum and to show them on the graph. Now, I'm not sure how much bother you went to here to do this, but this is how Raymond suggests you do it. So we have plotted the data up, and now we're holding on. So what we want to do now is show on. In fact, I'll just show it to you here. Whatever it is. It's here somewhere, I think. That's not what I want to show you. There it is, right? Okay. So here is the temperature for the month. And as you can see, it was quite a cold month. We hit -10. So what we're showing here is Raymond is programmatically showing the minimum, which was -10.02 degrees, and the maximum, which was 11 degrees. So actually, this was around Christmas Day. I don't know if you remember, a long time ago now. But something like Christmas Eve was freezing, and Christmas Day, the temperatures absolutely, relatively speaking, jumped by 20 degrees in almost a day. I mean, it was really dramatic. So how do you do that programmatically? So first of all, you find the maximum temperature, right? So we have the max, but we also know where it happened by putting in the index here. And then we plot at that point and that y-max, we put a marker, right? And then what we also put in is he puts in text beside the marker. So not only does he put a red dot, or a red O beside the maximum, it also puts in a piece of text close to that. So he says where to put it. So he creates a string to say the max temperature is whatever. And then he says where to put it. Can you read that up the back? Probably not. You can? Okay. And then he does the same for the main. So essentially you find the main, find the index, and then plot again another red mark, and then put the text in beside it. So essentially we get...
Will you be posting this up on the Blackboard as well?
Maybe I'll put this one up on Blackboard. Right. The problem with putting these up on Blackboard is that next year they all come back. Which happened this year. People were handing up solutions to last year's assignments this year and getting 0 for them because essentially we changed the assignments a bit. Yeah. But I will put this one up, okay? Right. So as you can see, there's our red dots and there's the text. Okay? So very nice. So I forgot about the arrow as well, which he put in. Alright, so this was the gold-plated solution, by the way. I didn't expect people to go to this amount of bother, but Raymond is a bit of a perfectionist. Some of you might know him from the lab. So, I won't say. Ah, yeah, I did. He's very good. Okay, now where did the editor go? Sorry. Where did the editor go to? Okay, let's move on. Alright, so then you ask the user, what date in the month were you born? I said, make sure you use a while loop. So in other words, while the date is less than 1 or the date is greater than 31. Enter the date, right? I would do it a bit differently, but that's fine as well. So he sets it to 0 at the start to make sure you go into the loop. And then he says, right, enter the date. And of course, if you enter, yeah, oh, that's fine. Okay, we found the date here. Now what we want to do is we want to extract the values relating to your date. So if you were born on the 12th of December, you want to extract those 24 values relating to the 12th of December. So in other words, we have a whole load of data relating to December for all the dates, for all the days of December per hour. We want to extract a subset that relates to your date. So we need to skip to that start point and then read 24 values. Right, so what do we do here? Okay, so he reads through all the temperature 1, which is the value every hour, and then he takes each 24th value, which would be the start of every day. So that gives you the start, and then he adds 24 to it to get the end. So you now have all the values for a day, which is your range. Okay. Now what you have to do is create third order and seventh order polynomials. Alright. So we use the polyfit, right? We give it 1 to 24, because remember it's during the course of that day, and we're giving it the actual temperature. And we want to use a third order. So it generates the coefficients, and then we plot using those coefficients. Alright? So we create the y values for those coefficients at these various data points. Then we generate the seventh order, and finally we plot everything. Okay. Alright, so we create a subplot. In the first one we're putting in the third order. In the second one we're putting in the seventh order. Okay? And in the third one then, I think we're putting in the part 2. Yeah, okay. So, shift down the figure. Okay, I think I want to show you here before I do that. Okay, so as you can see, the workspace gets fairly filled. So there's the actual data, where's the 44,000 values. And then we go through, there's our third order coefficients, our seventh order coefficients, maximum and min. Right. I need to go early today. Actually, maybe what I'll do is I'll put this code up actually on Blackboard, and I'll just finish off part 2 actually.
That's right.